Hello world viewers. What do you do? I hope all you are doing well and your viewers and viewers are also doing well. First of all, I convey my best regards and heartful thanks to all of you for watching this video. Good morning to those who are watching in the morning. Good evening to those who are watching in the evening. And good night to those who are watching in the night. So my name is Sudeepta. Today I am going to discuss about the crown of the equation. That is not only in the physics, that is also in every subject. That's the crown of the equation. That's known as del m is equal to E upon c square, or it is widely known that is E is equal to mc square. So today we are going to derive this equation, and at the end we are also discussing about the application of this equation. So let's get started without any further delay. Let's say there is a radioactive atom like uranium and thorium, and we know a radioactive atom every time splits some kinds of energy from outsides. Like uranium and thorium, it is happening in the nuclear plant, So let's say that is like a radioactive element. This is a radioactive element. It has a, let's say, mass m0, right? And it has some kind of energy that is, let's say, E0. Okay, it splits energy. Let's say it splits energy of a photon, that is small e, and it also split energy in the left side, that is small e. Okay, so what is the total energy emission? That is E is equal to E plus E, that's equal to 2E. Okay, we know it. Let's say this is the S frame. S frame. As this equation is from the relativistic theory of relativity, so these are the things to be needed. Okay, we know in the Planck's equation that is E is equal to h nu, where h is the Planck's constant and nu is the frequency. Okay, so what we can say, that is equal to Es. Here S means energy of emission in S state. Okay, so Es is equal to 2h nu. Okay, let's say this is our equation. Es is equal to 2h nu. What happened here? Here it has some kind of energy, that is E0, and it radiates some kind of energy, that is one photon energy small e and another also small e. So how much total energy emission? That is equal to 2e. E plus E, that is equal to 2e. Let's say after the emission it has rest energy, that is equal to E1. So E1 is equal to, we can say it is after emission. At first it has E0. E0 minus Es, that's equal to E1. E1 is the energy after emission. E0 is the energy before emission, and Es is the total emission. How much total emission? That is equal to 2E. So this is a relation we got from the S frame. Okay. Then we are going to STS frame. Okay. I forgot one thing, that here I am seeing. I am here, Sudeepta is standing here and is watching all these kind of things happening here. This is, let's say, Sudeepta. And he is seeing all these kind of things. Oh, these are things happening. Okay. Then we are going to the STS frame. What is happening in the STS frame? Let's say this. Okay, I remove it. Don't be worried, I will give you in the PDF form. After this video you will get all the derivation in the PDF form, so don't be worried. So in S frame we see that there is a person, that is Sudeepta, is seeing these are the things happening. Okay, in S frame. Then in STS frame, what happened? In STS frame, it is the STS frame. Okay, someone is flying in a rocket. Okay, let's say this is the rocket. Oh my god, this is my drawing. My drawing is not good enough. Let's say here someone is sitting, that is, let's say Einstein. Oh my god, this is a crazy boy, old, wise, looks crazy boy. This is Einstein. I'm sitting here. Oh, what are you doing? Hey, Sudeepta, come here. Then I'm coming to this. Okay, sir, Einstein. Hi, hello. Sir, I'm a big fan of you. You know to me? Yes, definitely I know. What you see? Oh, what we are seeing? Oh, we are seeing that there was a radioactive element and it splits some kind of energy. That is E. Okay. And the rocket is in the motion. That is B. Okay. In the relativistic term, what we can see? We can see the source also coming to us in the same velocity. The atom is also coming to us in the same velocity. So for us, this is STS frame. This rocket is the STS frame. What we are seeing? We are seeing that the source, this atom, is coming in the v velocity. Okay, in the v velocity. So Einstein says, I says, okay, what happened? The mass is that, at that time the mass is m naught. Oh, right. Oh, so here also the mass will be m naught. Einstein said, no, you forget something. You forget about the relativistic Doppler effect. You forget about the relativistic Doppler effect. And you also forget about when the body is in the motion, it gains some kind of mass as well. We know from the relativity equation that is equal to m is equal to m naught 1 minus v square upon c square root over. Okay, your m is in the motion. When the m is in the motion, that is relative mass, that is equal to the rest mass divided by the time dilation. What is time dilation? Time dilation is the gamma, that is equal to 1 minus v square upon c square. Don't to be worried, I will go to this derivation in the next videos. Okay, so don't to be worried this kind of equation. I say that I am describing about the crown of the equation. I am describing about the top of the equation. I will go to the low level in the next videos. Okay, so here Doppler effect plays a major role. We know about Doppler effect. What happened in the sound variation, we know it, right? But in case of light, how Doppler effect works, we don't know it. So don't know it means I don't want to describe that Doppler effect in this video. I will describe Doppler effect in the next video. Definitely in the next video I am going to discuss about the Doppler effect derivation. Here I just use the Doppler effect equations. What Doppler effect says, just at a rough point, I just want to tell. What happened in the A state? In the A state, it radiates energy. So how it radiates? Let's say this is the radioactive atom, it radiates. This is the wave, first wave, this is the second wave, this is the third wave, right? So here the same frequency, here is also same frequency, here is also same frequency, here is also same frequency. But what happens in the space frame? We are moving in the rocket. That means the waves are looks us in the different way. The waves will look us in the different way. How it looks? Let's say how it looks. It looks like this. Oh my God. You know what happened? This is the thing. This is the actual thing. As we are going in the rocket, that means it looks like it's screnched. It shrinked. Look at this. Look at the distance. Here. Right? We know there is a relation in the EM wave, that is beep gear. Okay? Here the bluish, here the reddish. When you go far away, it looks reddish and it looks bluish. So it is blue shift. Let's say. It is blue shift, it is red shift. Okay? Here the frequency is higher. And the wavelength is lower. Here the wavelength is higher. But the frequency is lower. Okay? So we are not going to the derivation at first point. And in the next video I am going to the derivation of the Doppler effect. Here I just use the formula. What is the formula? That is F blue shift. Let's say FB is equal to nu. That is the frequency. Normal frequency. What is happening in the S frame? That is C plus V root over upon C minus V root over. This is FB. Okay. What is FR in the red shift? That is equal to C minus V root over upon C plus V root over. So this is the frequency in the blue shift. This is the frequency in the red shift. Sorry, I just use nu. Okay, there is the nu. So we have the frequency. So we are also going to derive what is the energy also here. We are also going to find the energy, that is EB. Energy in the blue shift. What we have to need? This is the frequency. Just we have to multiply the Planck's constant. That is H. H nu C plus V root over upon C minus V root over. Okay, we got it. EB. What is EB? You got it. Then what is ER? Just we have to multiply the Planck's constant. That is H. That will be H nu C minus V root over upon C plus V root over. Okay. Oh, this is the thing. So what is H nu? Oh, h nu means happening in the S frame. There is something happening. That was the atom. That is a radioactive atom, and it splits some energy. It splits some energy. That is made, let's say, small e. And we know that in Planck's equation that h nu, so is equal to h nu. So we can replace h nu as small. We can replace h nu as small e. So EB is equal to small e c plus v root over upon c minus v root over. Okay, like that, ER is equal to small e c minus v root over upon c plus v root over. Okay, so what we see? We see in the S dash frame, it has some kind of energy. Okay, because it shifts as the frequency is higher, that means the energy is also higher. As the frequency is lower, that means the energy also lower. That we can see the relation, energy is directly proportional to the frequency. You can also see this relation E is equal to h nu, and h is the constant. That means what is the relation between the energy and the frequency? Directly proportional. If the frequency is higher, the energy is higher. If the frequency is lower, the energy is lower. Due to the Doppler effect, due to the contraction of the waves, that's why it increases the energy. And due to the lax contraction of the waves, that's why this is the energy. Okay, so what we have to find in the next step? We have to find how much total energy emission in the S dash frame. What is the total energy emission in the S dash frame? Okay, we have to erase this. Let's say in the S dash frame, it has some energy before emission, that is h naught. H naught is the before emission. It is the before emission energy. Before emission, let's say. And h1 is after emission. Let's say it's after emission. And the energy emission in the S dash state, let's say this is E S dash, emission of energy, total emission of the energy, let's say emission of energy. So what will be the relation? The relation will be simple like that. That is h naught, h1 is equal to h naught minus E S dash. h1 is equal to h naught minus E dash 1. Okay, so we will find what is ES1. That's why we have to find what is the total energy emission. Okay, so before it, we see that the energy happened in the blue shift, that is equal to EV, that is small e, yes, c plus v upon c minus v, that's root over, that's also root over. And ER in the red shift, small e, c minus v upon c plus v, okay, root over. So what is the total energy emission? ES1 is equal to ES dash in the S dash frame energy emission. ES dash is equal to energy in the blue shift plus energy in the red shift. What is the energy in the blue shift? That is small e, c plus v root over upon c minus v root over plus small e, c minus v root over upon c plus v root over. We can take common small e. Very simple calculation. All you know. What will happen? C plus v root over upon c minus b root over plus c minus b root over upon c plus b root over. Okay, this is a simple calculation, all we know. No need to describe a lot about this. Okay, the small e, c plus b plus c minus b upon c square minus b square root over. Okay, in the last step, that is equal to small e, that plus b minus b will be cancelled out, that is equal to 2c. Okay, if we take common c square, what will it reduce? That is c square 1 minus b square upon c square root over. What will happen in the next step? Small e, 2c divide c into 1 minus b square upon c square root over. Okay, so these are the things. The c and c will be cancelled out. What will the remain? That is equal to 2e 1 upon 1 minus b square upon c square root over. Okay, 2e 1 minus b square upon c square root over. What is 2e? 2e is nothing but energy emission in the S frame. Have you forgot this? ES is equal to E plus E, that is equal to 2E. So we can replace 2E as energy emission in the S frame. ES 1 upon 1 minus B square upon C square root over. So we have found a relation between energy emission in the S dash frame is equal to energy emission in the S frame into 1 minus B square upon C square. And 1 minus B square upon C square also known as time dilation. That is lambda. That is lambda. Lambda is equal to 1 minus B square upon C square root over. This is time dilation. This is the relativity theory and how the relativity contacts, how the Doppler effect happens. Then this kind of equation, this kind of relations happens, right? This is the beauty of this equation. And we are going to find that ground. Work is not done yet. We are going to do it. We are going to do it. Okay. Okay. We just look at the scenarios, two scenarios in a single frame. Okay. I just erase it. Okay. Don't to be so much worried about the notes. I will provide you the PDFs how the derivation work out very clearly. You just look at this. Just understand this. And one thing I also want to attach this. If you are a non-scientific background, don't to be worried. If you are a art student, if you are a commerce student, or whatever the students, or if you belong to science student, don't to be worried. Just enjoy this derivation, how Einstein thinks and how the things are going on, how a scientist thinks. These are the things we need to learn, right? So you can apply this on your various kind of subjects as well, not to be contract your mind in particular things. Okay, we are going to visualize those two scenarios in a single frame. I just erase it. Statements. Time. So we have two scenarios, right? And there is a frame known as S frame. There is a frame known as S frame. Okay. And there is a frame also, there is an S dash frame. Okay. These are the two frames. Here we say that there is a radioactive element. This is the radioactive element. It has a mass that is m naught. And it also has a radioactive element. That same radioactive element. What happens on that case? We are seeing this from a different frame, that is in the rocket. That is in the rocket. Do you remember it? Here Einstein is sitting and he also introduced me. Sudeepta is also sitting here with Einstein. And visualize those things. In the rocket, these persons are going in the v velocity. That means the same source, that same m naught source looks as if it is going in the east direction. Going this direction in the v velocity, in the same velocity. Okay, here we see that the mass is m naught. Due to it gain some motion, this mass converted to m. Let's say that is small m. Okay, these are the scenarios. It radiates energy that is small e. It radiates energy that is small e. So what is the total energy radiation? That is equal to ES, that is equal to 2E. We see this equation. Okay, here also what we see, that is ES dash, total energy emission. And what is ES dash? We find a relation that is equal to ES into 1 minus B square upon C square root over. This is the relation we got. Okay, and what are the other relation? That is, I say it has some energy before emission E naught, after emission E1. So what is the relation? E1 is equal to, what is the energy in the before emission minus after emission. This is the first relation. Okay, this is the first relation. And here also, I don't say 1. Here also, so same thing. That is, it has the energy after emission, that is H1, and before emission H0. That is H1 is equal to H0 minus ES dash. We have seen this equation before. Okay, so what we are going to introduce in things? What are the difference in these two equations? I mean two frames. That is the only difference. That is, it adds some kind of velocity here. Here it is in the rest. Okay, let's see, here it is in the rest. Here it is in the motion. Here it is the motion. That means what is the difference in this frame and this frame? It gains some kind of kinetic energy as it has the motion. You know, when a body get kinetic energy when it is in motion. So the same thing. So what we can relate? What we can relate here? Very famous things we are going to introduce here, right? Here H naught minus E naught. What is H naught? H naught means energy before emission in the S frame, and E naught energy before emission in the S frame. So what we can see, H naught minus E naught is equal to change in is equal to kinetic energy in before emission plus the constant. I don't take C. If I take C, then you will say this is the speed of light or velocity of light. I will take beta. Okay, I will take beta. So it is the emission. Before emission, the energy in the S dash frame. Before emission, the energy in the S frame, that is equal to some kinetic energy before emission. Some kinetic energy before emission. Same thing. H1 is the kinetic energy. Sorry, H1 is the energy after emission of that atom. Then minus E1. E1 is the emission after that. Okay. What is that? That is equal to some kinetic energy after emission. Some kinetic energy after emission. Let's say this is also constant beta. Let's say this is the equation 1. Let's say this is the equation 2. Okay. This is the equation 1 and this is the equation 2. If we differentiate, if we equation 1 minus equation 2, okay, if we subtract equation 2 from equation 1, if you subtract equation 2 from equation 1, what we have, that is H naught minus H1, okay, H naught minus H1 minus E naught minus E1, okay, E naught minus E1. Do you look it? H naught minus H1 minus E naught minus E1, okay, that's equal to kinetic energy before emission minus kinetic energy after emission. Now beta will be cancel out. Okay. What is H naught minus H1? H naught minus H1. Look at the relations. Where you find here. Here we can see H naught minus H1. H1 will go to that, and ES1 come to this place. It will go to the right hand side. It will go to the left hand side. It's very simple. ES dash, that will be ES dash minus E naught minus E1. E naught minus E1. That is equal to ES. Okay, that is equal to ES. That's equal to what is that? Let's say this is the difference in kinetic energy. Let's say this is the difference in the kinetic energy. Let's say this is del. Let's say this is del K. Change in kinetic energy. So we got a relation, that is change in kinetic energy. So we saw this. Your ES dash minus ES is equal to change in kinetic energy. What is ES dash? There is a relation. ES dash is equal to ES into 1 upon 1 minus B square upon C square root of. Okay, simply we just apply those relation here. What is that? That is ES dash is equal to ES. Okay, let's say that is ES 1 minus B square upon C square root over, okay, minus ES, that is equal to change in kinetic energy. Look at this. Any doubt? I just replace this into that. I just replace this into that relation. Simple. I can take the common. That is ES. What is ES? ES is the energy emission in the S frame. Okay. ES. If we take it, what we can write this? 1 by 1 minus B square upon C square 1 by 2. Do you know it? We can take root over of A as, you know it or not? Okay, this is the symbol. Minus 1. Okay, that is equal to change in kinetic energy. Okay, the simple process will happen in the next step. ES into, if the power will go to the denominator side, what will happen? If we go to the numerator side, what will happen? It will be minus 1 by 2. So what will happen here? 1 minus B square upon C square minus 1 by 2 minus 1. Change in kinetic energy. Oh my god, what is the equation? There is binomial expansion. Oh, so it is a formula. crazy things, the formula to remember. No, don't need to remember here. We just think some things. Oh, we will say, what, yeah, these are equation. Where will you find this equation? 1 minus b square upon c square to the power minus 1 by 2. Oh, here the binomial expansion is happening here. Don't need to talk. Don't need to worry about. Just visualize something. I just want to describe you. Don't to be so much worried about not. I tell you about this. Okay. So this is 1 minus. This is 1 minus b square upon c square to the power minus 1 upon 2. So you say, what will be the application of this? Just see the simple things. Just see the simple things. Actually, what is the formula for this? I just want to tell you. 1 minus b square upon c square is equal to what will you see? That is 1 plus half b square upon c square plus 3 upon 4 b square upon c square plus 5 upon 8 b square upon c square cube plus 7 upon 16 b square upon c square 4. So we'll say this is the equation I have to remember. Not need to remember. Not need to remember. I just want to see things. 1 minus x square, that is equal to 1 minus 2x plus x square. Okay. 1 minus x cube. How it happened? We all know binomial expansion. Don't to be worried. I am going to derive the binomial equation as well from the mathematics section. Don't need to be worried here. That is 1 minus 3x plus 3x minus x cube. All we know. It's like the same thing. 1 minus b square upon c square to the power minus 1 upon 2. That is 1 minus. Then the equation comes. That is minus 1 upon 2. Minus 1 upon 2 into who is the x here? That is b square plus c square. Don't need to be worried about the others. Just fast step with just 1 minus plus 1 upon 2 b square upon c square. Something. B square upon c square something. Okay. Like this. But what happened here? Here b is very, very smaller than c. b is very, very less than c. That means, what will be the value of v upon c? The v upon c, if the value is vq, v4, c4, then the denominator will increasing a lot, and it will be very less and less as compared to this. Let's say here it is a very big number and here is a very small number. So it is very, very less than 1. In the physics, we can also eliminate. We can also neglect those kind of things. So here we can neglect these terms as b is very, very smaller than c. As we can say x is very, very smaller than 1 in the binomial expansion. Then we can neglect this kind of equation. Also we neglect every equation in the classical mechanics. You all know when something is fallen out, we will neglect the gravity. In physics it is very natural things. Neglection will be looks very complicated things. How you can neglect those kind of things? But in physics it is very simple. It is very simple and neglect this kind of situation. If we say the constant things, there is nothing constant in the universe. Everything is in the motion. Okay, so we took constant, we assume constant, but nothing constant in the universe. Even the earth is moving, the sun is moving as well, right? So here we can have facilities that we can neglect those kind of things. So what we can see in this form, that we can apply these things. That is what? 1 minus b square upon c square to the power minus 1 by 2, that's equal to 1 plus 1 by 2 b square c square, right? So here we can see E is, what we can apply here, that is 1 plus half b square upon c square minus 1. I neglect these kind of terms. I neglect these terms. Okay. Minus 1. These are the terms. I apply this. Minus 1. That is equal to del K E. Change in kinetic energy. What we can see? Here 1 cancel out. You can see it. You will do it. I don't do it. Okay. Next we are going to the next step. Okay. You understand from this point? Okay. from here we are going to look at this. Okay. So here it is ES 1 and 1 cancel out, that is 1 into v square upon c square. Change in kinetic energy, what does it mean? Change in kinetic energy, that means half. Change in kinetic energy, what it refers, that is what is the difference between this kind of energy. Okay, half mv square in the s frame minus half m naught square in the s dash frame. Okay, b will be the same, okay, because that is the motion, that is the first frame, that we are seeing something in a very a rest frame. In the rest frame we are seeing the rocket is in the rest frame. Oh, these are the things happening, oh, these are the things happening. Then some emits some energy, then the mass will be m. When it is the motion, the mass will be m. Firstly it is m naught. Okay, so what you can take, that is half b square with the common, what will the remain, m minus m naught. Okay, here es into half b square upon c square. Look at the things, we are the ending point. We are on the ending point to reach that equation, that universal equation. We know from a very big points we waiting for, very big times we waiting for this equation, to derive this equation. This is world famous equation. Can you feel my enthusiasm to this? Can you feel my energy level to this? Can you feel my curiosity to this, to know it? Okay, just look at with me. Okay, here half and half will be cancel out from the both side, and v square will be cancel out. What is m minus m naught? M is the mass when it's in the motion. We are seeing from the rocket to that rest level that the object is moving towards us. Then it gains some mass. This is the relativity. It gains some mass. So this is nothing. This is the increment in the mass. Let's say this is del m. Okay. Here the half and half will be cancelled out, and v square will become cancelled. So Es upon c square is equal to del m. What I symbolize this? This is del m. Yeah, this is the required equation. What we are going to derive? Okay, del m is the increment in the mass, and Es is the energy, which is splitted in the s frame. Okay. In the end, Es is equal to del m c square. Look at this. This is our required equation, and it is also known as E is equal to mc square. Look at the equation. Look at the derivation. We got this point. We got the derivation. In the next point, we are going to see the applications. And it's very simple things. I just want to tell you. In 1905, Einstein published this theory in very few pages. What it tells actually something different. So, I mean, the energy we replace in E, we denotes in E, but he denotes in L. It is his style to represent, it is my style to represent E. I tell energy as E, he tell energy as L. I will also replace you what he has seen in the published theory. Okay, I will show you in the last of this video. Before that, I will tell the application. Okay, what is the application of this equation? Look at the derivation. Did you feel the energy? The equation that is equal to mc square. Now it's the time to know the applications. Okay, application is very big point here, because we are stick on this point. Yeah, we are doing those kind of things. What are the applications saying? Okay, the applications are here. What are the applications? Let's see. There is a view. E is equal to mc square. The equation we find it out. Again, I am saying E is equal to mc square. Okay, what is we get? Es is equal to del m c square. This is actually your del m is equal to Es upon c square, the actual equation. Del m is equal to Es upon c square is the actual equation. What is the application? Look at this. We got different kind of electricity nowadays. we got thermal electricity, right? Then we got hydroelectricity. Then we got other source of energy also, wind electricity also. Wind energy we also got, through that we also get wind electricity. Okay, from thermal, from hydro, that is water, and from wind. And also we get from nuclear electricity. Nuclear electricity. So from this, the most effective is nuclear. From some quantity, we can get a large amount of energy in the nuclear energy. But here, what happens? In the thermal electricity, we got the electricity from the coal. Till this date, we got 70 to 80% of the electricity from thermal. Don't you look, it's crazy. It's very much effective to the air pollution as well. Nuclear electricity is the best, I can say till date. If we go to the equation, look at the E is equal to MC squared. Let the mass is 1 gram. 1 gram mass, how much energy it can give? 1 gram mass is equal to 1 gram. That is equal to this. And C is 3 into 10 raised to the power 8 meter per second. Okay, 3 into 10 raised to the power 8 meter per second. That's E is equal to 1 gram into 3 into 10 raised to the power 8 meter per second square. Okay, so what is the value of this? 1 gram 3 square 9 into 10 raised to the power 16 meter per second square. Okay, so what is total? 9 into 10 raised to the power 16 joule. From 1 gram of energy, we can get these kind of joules. Can you imagine this scenarios? You can fulfill many cities, many state electricity from a single days or 2 days or 3 days or 4 days, 6 days, 7 days. If we can reach the maximity level of this equation, then we can get those kind of energies from a single 1 gram of mass. I believe in my technology 100%. One day I will reach the top notch level, but today's date. But nowadays the equation is just here to estimate how much nuclear energy comes from. That is, it is happening in the nuclear power plant to estimate the energy, how much energy it can give. Okay, this is the helpful in this equation nowadays, but it can give more and more applications in the future. I guarantee it. This equation will help us a lot. Okay. Secondly, it is also used in the medical treatment, like the CT scans are happening, the equations in the medical sections. This equation also happen in the CT scans, the cancer scans, the bone scans also affecting this equation. This equation is affecting on those areas also. Okay, and the third, in the GPS sector, this equation also plays a major role. In the GPS section, this equation also plays a major role, and also it is also very essential to exploring the universe. Look at the equation. It is the energy, and it is the mass, and it is the speed of the light. The relation, that is, mass is nothing that is equivalent to energy. Mass is nothing that is equivalent to energy. That means mass can be converted into energy. Energy can be converted into mass. If it loss of energy, it means it lost some mass. If it lost some mass, it means it lost some energy. The same thing, it's also happening how the exploring universe, how we can find it out different kind of things, because this is the law of the nature. This is the laws of the nature which is represented in the equation. Okay, that means in the whole total universe, these equations is happening. The same laws is happening in everywhere, not only in the earth. It is also happening in the Mars, in the moon, in the Saturn, in Milky Way galaxy, in other galaxy, in the black hole. Other things also, these kind of things are happening. Okay, so these are the scenarios, these are the application, and it will also apply more and more in the next level. Okay, we know the applications, right? Then at the end I say that in the 1905 what Einstein published in a 3-page. I have that document. You can also find it is spread in every internet, and if you can't, I also provide you. Okay, I just want to show you those things. At first, what he says that the results of an electrodynamic investigation published by me recently in the journal lead to a very interesting conclusion, which shall be derived here. There I based myself upon the Maxwell-Hodge equations. So look at the things. He used the Maxwell-Hodge equation, he used the Doppler effect, he used the previous null scientist. Don't say that only Einstein derived this equation. Einstein also helps take the helps of other scientists as well, right? So after that we can get this crown. Okay, to get this crown we have to need to know the speed, we have to know the velocity, we have to know what is mass, we have to know what is time, we have to know what is the speed of light. Its speed of light is constant or variable. Various things are to know this, but I tell you from the top side, I tell you from the crown side. Look at the equation. If you see what Einstein describes, you will be very shocked. Look at this, look at this, look at this. If it is look at this, this is k naught minus k1 equal to L upon v square into v square upon 2. Here v is the speed of the light here, and L is the energy. Look at L is the energy here. Here L is the energy. Okay, here look at this, L is the energy and v denotes to the speed of the light. So not need to be very essential that what actually Einstein says. It is not about what symbolization he fixed out. He is from a Greek background. His mother tongue is Greek because he is he's a Russian, I think, kindly, Nazis. So what is the language, what are those signs we use? It doesn't mean that we use E, we use E as E, he use E as L, I use E as S, whatever I can like. But I just have to describe that I use energy as S, I use energy as L, I use energy as E. Okay, so the same things at the reference. Don't to go to the symbolization a lot. Just look at what is happening behind that. Okay, and who are the scientists also give them a lot of supports. If there is no magnetism of the Maxwell, there is no E equal to mc square. If there is no classical mechanics of Newton, there is no E equal to mc square. So everyone has the role. Don't forget about the past, because the past gives us that kind of energy. We get this equation, from this equation we can achieve more and more. So we don't have to hesitate this kind of equation. Okay, if we in the future we get something new, it doesn't mean that we neglect those kind of equations. We also praise the past who has done for us. We have praised our forefathers because they are done for us a lot. Okay, the video is concluded here, and if you have any kind of doubt, you can ask me in the comment section. I will try my best to give you the accurate answer. Okay, I will definitely give you the accurate answer. If you find any kind of confusion regarding this equation, any kind of confusion regarding these problem solving equations, then you can comment me in the box that is in the below this video. You can comment it. I will definitely answer you. If I will definitely answer you. So here I end my session by saying thanks you for watching this video.